Hi, so in this video we are going to be talking about how we can use these fundamental trig identities. I want to remind you at the beginning here, we have our list of fundamental identities over here. I highly recommend that you memorize these, but in the process of memorizing them when you're working on these kind of problems and on your remote assignment for tonight, have a list of these Pythagorean identities, the even and odd identities, the reciprocal identities, and the quotient identities, because these are going to be our tools that we're going to use to work with these expressions. Okay, so it turns out that when you take calculus, maybe also when you take physics, but I think one of the main places where you will see the use of using fundamental identities is going to be in your calculus classes, and for those of you that go on and take Calc 1, 2, and 3, you will definitely be using this skill that we're going to talk about in this video. If you take differential equations, you will be using the skill we're going to talk about in this video. This is a big skill to have. Okay? And the skill that we're talking about is the idea of being able to manipulate a trig expression. So the instructions that I have written up here are, we are going to use the fundamental identities to simplify each expression. So our first example, the expression that we are looking at is cosine of x times cosecant of x. Okay? And our instructions tell us that in these examples, each expression simplifies to a constant, a single trig function, or a power of a trig function. So sometimes it's hard to tell, like, what do we mean by simplify an expression? Because that doesn't look that complicated right now. It's just a bunch of letters together. But our goal is to rewrite this expression so it can be written as either a constant, meaning a number, an individual trig function. Right now we have two trig functions, or a power of a trig function. I don't see either of these being an individual trig function being raised to a power. So we have some work to do. Okay, so looking at what's going on here, I don't know what I'm going to do, but I can at least write down an equals sign and say, okay, how am I going to change this expression? Well, over here on this fundamental identities list, one thing I see is that cosecant of theta is the same as 1 over sine theta. Okay. A good rule of thumb, and this is not always true, but if you're walking down the street and you're hanging out with Ariana and you're like, I think we should simplify some trig expressions today, and you come across one like this and you say, how can I simplify this? If you have no idea where to start, one way to start is by turning everything into sines and cosines. Well, here I already see a cosine of x, so I'm going to write that down. And cosecant of x is the same as 1 over sine of x. Cosecant of theta is 1 over sine theta. So I'm using this identity and replacing cosecant of x with 1 over sine x. Here I have x's instead of thetas. It doesn't matter as long as you're consistent. Okay, so now I look at this and I ask myself, okay, I see cosine of x times 1 over sine of x. Can I combine these? And the answer is, well, yes, I can. I can multiply these. What I want to think about is this is really cosine of x over 1. And now I can multiply across the top. Cosine of x, multiply across the bottom, sine of x. So now I have cosine of x over sine x, and I ask myself, does this remind me of any of my trig identities? And the answer is yes. I see cosine of theta over sine theta, and that's the same as cotangent of theta. So I can replace cosine of x over sine x with cotangent of x. And now I have rewritten cosine of x times cosecant of x as one trig function, and so we are done. Okay, so that's our first example of simplifying a trig expression. We're going to go through a couple of examples. I think for me, sort of thinking about these is the hardest part, is figuring out how do I want to think about these particular expressions. What's a way to simplify them versus what is the best way? And the most important thing is find a way. There's not necessarily the best way. There are often many, many different ways to simplify a particular expression. So as you're watching me look at these expressions and you're watching me simplify each of these expressions up here, if you think, wait a second, I would have done this other thing, try it. And if you get stuck along the way, or if you try it and it does work, shoot me an email. You could use that as your point of contact and say, hey, I tried simplifying doing this. Will that work? Okay. All right, so here's our second example. Our second example we have is sine squared theta times cosecant squared theta minus 1. Okay, so our job is to simplify this expression, and I do see a couple of things. One option is the strategy that we talked about on this first one, where our strategy over here was maybe to try to turn everything into sine of x's and cosine of x's, and then see what we can do from there. Okay. And that is definitely an option up here. Okay. And maybe we'll come back to that option. That's one strategy. Another strategy is to look at this expression we have up here, sine squared theta times cosecant squared theta minus 1. And what I notice here is that I have a trig function that's being squared, and it's paired with a 1. Okay. That kind of reminds me of one of those Pythagorean identities. So I'm going to go over here and take a look. The Pythagorean identities that involve cosecant, that's this guy down here at the bottom. That's the one that's part of your remote assignment to derive this one. But it's not quite what we have written up there. I'm going to write down the Pythagorean identity over here, and we can stare at it for a minute. The Pythagorean identity is that cotangent squared of theta plus 1 is equal to cosecant squared theta. Okay, so it doesn't look exactly like what's inside here, but what's cool is this is an equation, and I can manipulate that equation. And so if I were to say subtract 1 from both sides, I would have cotangent squared theta is equal to cosecant squared theta minus 1. So now, instead of cosecant squared theta minus 1, I can replace that with cotangent squared. All right, so what does that give me? That gives me sine squared theta times cotangent squared theta. Okay, that's a thing. The question is that any better? Unclear. What do you think, Ariana? She's speechless. Okay, so looking at this, I don't know where to go from here, so I might try the strategy of turn everything into sines and cosines. Well, this guy on the outside is already in terms of sines and cosines. Cotangent is cosine over sine. So cotangent squared will be cosine squared of theta over sine squared theta. This seems like a good idea. I think we should keep going. All right. We've got sine squared theta times cosine squared theta over sine squared theta. And when I think about this, our first sine squared theta is over 1. So I can cancel the sine squareds on the top and the bottom. And what I'm left with, all that I'm left with, is cosine squared theta over 1, and I don't need to write the over 1 part. So we have now simplified our original expression into cosine squared theta. Okay, now I want to point out that there are a bajillion and one different ways that we can work on simplifying this stuff. So I want to talk about an alternative for this same example. this example where we started out with sine squared theta times cosecant squared theta minus 1. Okay. All right, so I felt all cool over here at the beginning because I said, oh, look, inside this parentheses kind of reminds me of this Pythagorean identity. And once I write down this Pythagorean identity, I can manipulate it to make it look like what's inside the parentheses and then do a substitution. So that was kind of cool. I was like, oh, look, I can use my Pythagorean identity. If I didn't see that idea at the beginning, here's another way to think about this simplifying. Okay, I look at this and I say, I have no idea where to go. If I have no idea where to go, then what I want to do is I want to turn every term into sines and cosines. So here we have a sine squared theta on the outside. Cosecant is the same as 1 over sine theta. That's one of our reciprocal identities. So cosecant squared is the same as 1 over sine of theta squared. I can distribute the square to the top and the bottom, so this becomes 1 over sine squared theta, and then minus 1. Okay. Everything is in terms of sines and cosines, but there's no cosines here. If I distribute this sine squared theta from outside the parentheses into the parentheses, first I end up with sine squared theta over sine squared theta. And my second term is minus 1 times sine squared theta. Okay? So sine squared theta over sine squared theta is 1. And so we have 1 minus sine squared theta. And now I'm a little bit, I want to pause here because at this point I've rewritten this initial expression. It's already in terms of sine. There are no fancier trig functions going on. So I have to ask myself, does this expression right here look like anything that I know? And the answer is, it sure does. This guy right here, it's got a sine squared, it's got a 1. Kind of reminds me of cosine squared theta plus sine squared theta equals 1, the best trig identity in the entire world. I want to manipulate this identity so part of it looks like 1 minus sine squared. So how can I do that? Well, I can subtract sine squared from both sides. So I end up with cosine squared theta is the same as 1 minus sine squared theta. This is cool. I've got a 1 minus sine squared theta. That's the same as cosine squared theta, so I can replace 1 minus sine squared theta with cosine squared theta. Same final answer, 2 different ways. All right, we're going to pause here, take a break. Thanks for listening. We'll be back in a few.